In this lecture, we are going to learn how to analyze series RLC circuits, particularly the natural response of a series RLC circuit. So let's consider, again, that we have a practical voltage source with an independent voltage source Vs in series with a resistance Rs connected to a switch. That switch is again going to open at t is equal to 0. And we're now going to have a network where our resistor, capacitor, and inductor are all connected in series. So I'm going to define the inductor current as flowing down. So this will be my inductor voltage, VL of t. I'm going to define my capacitor current as flowing up. So this will be VC of t. And I'm going to define my resistor current as flowing to the right. So this will be VR of t. The reason why I've chosen what might look like an odd assortment of directions for my currents and polarities for my voltages is that I know once this switch opens up, we're just going to have all three of these elements connected in series. And so I'm trying to make it to where my current is the same around the circuit. So IR flows through this inductor current, IL flows through this capacitor, giving us IC. They're all going to represent the exact same quantity. So as far as our analysis goes, it should be easy to see that when this switch is closed, this guy is going to look like an open circuit. So current isn't going to flow through the capacitor. Some current will then flow through the resistor and the inductor. So the inductor will have stored energy. Because there's current flowing through the resistor, our capacitor will also have stored energy. And after our switch opens up, our inductor and capacitor will distribute its energy to the resistor, which will convert it into heat. So let's write a Kirchhoff's voltage law equation where we're going to start at this bottom left-hand corner. So we should see VC of t plus VR of t plus VL of t is equal to 0. And we're going to express everything in terms of this inductor current IL. After the switch is open, all three of these currents are going to be the exact same thing as the inductor current. So VC of t will be 1 over c, the integral from t naught to t of IL of x dx plus some initial condition on our capacitor voltage. The voltage drop over our resistor will just be R times IL of t. And the voltage drop over our capacitor, our inductor, will be L dIL by dt is equal to 0. We have an integral differential equation. We are going to take the derivative of both sides. So that's going to give us 1 over c IL of t. The derivative of the constant is 0 plus r times the derivative of IL of t plus L times the second derivative of IL of t is equal to 0. And we're going to divide both sides by L and rearrange slightly so that we get DIL squared by dt plus R over L di by dt plus 1 over LC I is equal to 0. So this is our second order differential equation. Our guess value is IL of t is going to be of the form A e to the st. If we substitute this guess into our differential equation, we get s squared A e to the st plus r over L s A e to the st plus 1 over LC A e to the st is equal to 0. Factoring A multiplied by s squared plus s times r over L plus 1 over LC e to the st is equal to 0. And again, we have the second order polynomial as our characteristic equation. So using the quadratic equation to solve it, we should find that S1 and S2 are simply negative r over L plus or minus the square root of r over L squared minus 4 times the coefficient of the s squared term, which is 1, times the coefficient of the constant term, 1 over LC, divided by 2, which is going to give us negative r over 2L plus or minus the square root of r over 2L quantity squared minus 1 over the square root of LC quantity squared. And we can see then that alpha for a series RLC circuit is r over 2L, and omega naught for a series RLC circuit is the exact same, 1 over LC square root. And from this point on, the analysis of the circuits is the exact same thing that you did with a parallel RLC circuit. So when alpha is greater than omega naught, the circuit is overdamped. When alpha is equal to omega naught, the circuit is critically damped. And when alpha is less than omega naught, the circuit is underdamped. You will do the analysis in the exact same order. So you'll determine whether it's critically damped, overdamped, or underdamped. Analyze the circuit at t is equal to 0 minus. Analyze the circuit at t is equal to 0 plus. And then, depending on what quantity you want to solve for, you'll use, say, the inductor current and the inductor voltage relationships to get you everything, or the capacitor voltage and the capacitor current relationships in order to solve for everything, just like we did in the previous problem. So really, fundamentally, the only difference between a series RLC circuit and a parallel RLC circuit is the fact that alpha is slightly different. That's it. Thanks for watching.